Okay, let's recall. Today we're going to talk about directional derivatives. So before we do that, though, I want to talk about partial derivatives, which are, you'll see in a minute, are very clearly related. So we'll recall here that if you take the x partial with respect to some function f, this gives you the rate of change of f in the x direction. And similarly, if you take the y partial at some point x naught, y naught, this gives us the rate of change of f in the y direction. So it makes complete sense to talk about finding the rate of change of f in any direction. So we're going to define this idea for any direction. And basically what we're finding is the slope of a tangent line at a point that's not parallel to the y or the x-axis. It could be in any direction. So here, let's get a picture up here. Try and make this as perfect as I can. Use my ruler. Okay, go away. So we have the z-axis, the y-axis, and the x-axis. So it's kind of similar to the last round. I'm gonna have the chunk of some surface here. So this is gonna be the surface z equals f of x, y, and we're just looking at a swath of this thing, okay? And then we're going to come down here to the oops, what happened? Got the wrong width. There we go. We're going to come down here into the xy plane and define a point p naught, which has coordinates x naught, y naught. And we're going to define a line through here. Call it cap L. And this is a line through P naught. It's not necessarily, I tried to make it look, so I'm not assume that it's parallel to the x-axis. It could be any direction, and this is going to help us with this idea of direction. Okay, so if we project the point P naught up, it intersects the surface z at some point z, well, x naught, y naught, z naught. Okay? So, and this is just f of the point, this is the point x naught, y naught, z naught. I'm sitting here trying to point with my pen and no one can see it. Okay, so getting back to the theory piece of this, as p moves along this line, I'll just pick some point along here, p of x, y, just to say it could be anywhere. As p goes along this line, and you evaluate all those points, a curve gets cut. So this is the point p of x, y. So as the points x naught, x, y go along this line from here to here, it carves out a curve C in the in the surface z of xy. And we're interested, we want to know, I want to keep this picture up here. We want to know the rate of change. We want to know dz ds, where s is this directed distance defined to be the norm of p naught p. Okay, so we want dz ds, the rate of change, and this will give us the derivative parallel to this line L here in this direction like that. So this will give us the slope of this line, the tangent line, to whatever point you're hitting on that. Okay, so to that end, we're going to define, we're going to let u be the vector u1 comma u2. Let me clean that up. Try again. U1 comma U2, right? And this is a unit vector with endpoint or initial point with initial point P naught. And this thing is in the direction of P. Oops, P, i.e. this P. Okay, so when I make this, I'll use green. So what I've done now is I've defined this line. I've put my P naught and my P along the line. That's just any point along the line. And now I'm saying, all right, I'm going to build a unit vector right here, U. And I couldn't put another color on top of that, so I just put it. But it's supposed to be, it's along this line. So this is my U. I guess that'll work. Come on. There. All right. So now we have. So this is U. It's a little unit vector, length 1, starting at P naught and going in the direction of P. Okay. So what's important to note here is that the vector P naught P, right? The vector that goes from P naught to any P is equal to this distance distance parameter times U, right? And if you look at this picture up here, this is saying P naught P is just equal to U times whatever distance brings it out to P. And that distance is in terms of S. Okay. Or, so the vector P naught P is X minus X naught, Y minus Y naught. If you just think about, you're in the XY plane, so it's just the slope of the line. And SU is equal to SU1, SU2, because scalar multiplication is defined in vectors. And so if you just take S times U, you multiply the components of U by S. Okay? So this gives us a system of two equations. X minus X naught equals SU1, and Y minus Y naught equals SU2. So this says that X equals S naught plus SU1, and Y equals Y naught plus SU2. Okay, this should look very familiar. We're working in the XY plane, so there's no Z coordinate. But this is just a parametrization of L using this S parameter. So what I've done is I've just parametrized this L using this S parameter. Okay, and L is in the direction of U. Okay, so L is in the direction of U. Well, U is actually on L, so it must be in the same direction. All right. Now let's go back to the curve for a second here. The point corresponding the point on C that corresponds to any P on there is f of x naught plus SU1 y naught plus SU2. Okay, so this is now any point on that curve C. I'm going to go back up here. So any point on this curve C has that value. Okay, so now we're going to compute. So now we compute dz ds. Okay. All right. So this equals, using the chain rule, it's f partial times dx dx plus y partial times dy ds. This is using the chain rule from the last video. All right. But P of x naught, or sorry, P naught, x naught, y naught. I'm going to go back up here. I can't keep the picture. So this point right here corresponds to where s equals 0. So this corresponds to s equals 0 on our parametrization. So when we evaluate dz ds at s equals 0, at that point, we get, writing out all the grimy details, we get the partial with respect to x of the point P naught times U1 plus the partial with respect to y of the point times U2. Okay. And this is the directional derivative of f of xy at P naught in the direction of U, which is our unit vector. Okay, so let's get some color in here. So this is, oops. This is it. So this is the derivative of the directional derivative definition. A lot of D's in there. Okay. And you can write it a couple of ways. I like to write it like this. It's cap D with a subscript U vector to tell you you're going in that direction of the function f at x naught, y naught. Okay. You can also put a z there instead of the f, and that just says that you're on the surface, but I like this better, and this equals exactly what's upstairs there. Okay, let's just back up for a second here and make a note. This needs to really jive with what we did before. So if u, the direction that we're considering to take the derivative at, equals I, right? Then the directional derivative with respect to u of any function is what? Well, if you think about that for one whole second there, you get that it's just the derivative, the partial derivative at x naught, y naught. Which is exactly what we said before, is the derivative in the x direction. Similarly, if we consider u to be the vector j, then the directional derivative of f is just the y partial. Okay. At a point. Okay, so what we want to also point out here, and this is key, this directional derivative is just a dot product of two vectors. So if you look at this thing I have in red up here, and you go backwards, what you have is you have the vector f sub x, comma x naught, y naught, comma f sub y, comma x naught, y naught, dotted with u1, u2. And so if I asked you to dot those two, you would get this. So we had this, now I'm running that thing backwards. Okay. And so this vector is a special vector. It's the gradient vector. It's called the gradient of f of xy. Okay. And some of you may work with this in other courses or in your physics courses. I'm not sure, so I'm just gonna do. It's always uses this symbol, which mathematicians call del f, and it's just this vector, the gradient of f. Okay. So this is a nicer way to write it. And then you say, okay, so the derivative, the directional derivative in the direction of u is just del f, oops, it's just del f dotted with u. Okay. Well, I had to get all that out, so there it is. Now let's do an example here. Let's do an example. So I want to find the gradient of the function f of xy equals 3x squared y at the point 1, 2, and the directional derivative of f in the direction of u, which equals 3i plus 4j. Okay, so first example with gradients and directional derivatives. Okay. So part 1 says we want to find del of f and evaluate this at 1, 2. Okay, so let's see here. So we have 6xy I plus 3x squared j evaluated at 1, 2, which is equal to what? 12i plus 3j. Okay. Now everyone listen closely. This is where a lot of mistakes happen. Part 2 says we want to find this guy, right? And this is the dot product of this guy dotted with u. And let me fix something here. I'm gonna make this vector up here go away. I'm gonna call it A. Why? Because I'm using a u down here. And that u is important. It's the unit vector in the direction of A. So we have to find the unit vector in the direction of A. So this guy needs to be normalized, which means it needs to be made length 1. All right, the length of the vector is 5. Think of a 3, 4, 5 triangle. And so the u I want turns out to be 3/5 I plus 4/5 j. All right. So how many times have I graded this? And when it comes time for a quiz or a test, instead of finding u, which just means you're normalizing the vector that you're given, people plug in the vector they're given. And then if you have to do anything else afterwards, all your computations fall to pieces. So just remember, take a second. I normally put a little reminder on quizzes and stuff where I go, hey, if you're going to compute a directional derivative, make sure you unitize your vector. Okay, so now let's compute this. So it's 36/5 plus 12/5, which is 48/5. And what's that, like 9 point something? 9.6. It's a very steep. All right, so this number is, it's the slope of the tangent line at 1, 2 in the direction of A. Okay. So these directional derivatives and gradients are huge, and we use them a lot in the days to come. So here's a theorem that helps out tremendously when you're doing computations. So we go I can't get this right, let f of xy be differentiable at some point x naught, y naught. 1. If the gradient at f of x naught, y naught equals 0, then all directional derivatives at x naught, y naught are 0, because you're always going to be multiplying by a 0 vector. If it's non-zero, then if it's non-zero, then among all possible then among all possible directional derivatives the derivative in the direction of del f, right? In this case, del f equals the a I just had a minute ago. Has its largest value so let me read this again. If the gradient vector is non-zero, then among all possible directional derivatives, the derivative in the direction of del f has its largest value. And namely, you actually get a number here. It's the norm of del f. Okay. All right. 3. The derivative in the opposite direction from 2 has the smallest value. Namely, minus the absolute value of del f at x naught, y naught, right? So it's the negative. This is a negative, right? So it's the smallest. Okay. All right. All right. How long is this going for? All right. So we're doing good here. This is a very, very dense, very dense section. So, okay, let's look at some pretty pictures here. Actually, let me do this. I'm gonna let f of x, y be a function. So if f of x, y equals a constant, then this defines a level curve of the surface. And if we were in class together, I would bring in a topographical map. I have some still left over from when I was a Boy Scout, because that's all you're looking at when you see a topo map. So to get ready for some fun drawing here. All right. This is y, this is x, this is z. Let's just make a fun curve here. That's the domain, and this is just a random surface. Z equals f of xy. Now, if I here, and I'll put a number here, 3. Okay, so if I go f of xy equals 3, then what happens is I fix the outside. So at 3 here, I get a contour line, right? And similarly, if I said let f of xy equal 5, which is up here, I also get this one at 5, right? Or if I let f of xy equals 1, which is down here, I get this surface here. not surface, sorry, curve along the outside. And so if you could think, I guess, I don't know, think of a mountain, and let's say I was looking at this guy, f of x, and I just looked here. If I chopped the top of the mountain off, so if I took all of this off and looked down on top of it, that would be the level curve. And what you do here is you project level curves onto the XY plane. And that's just a topographical map, literally, right? If you think about it. Okay. And so maybe for this example, if I said, plot the level curves of this on the XY plane, you would go like that, and you'd go like that, and you have X and Y. And so the first one would be probably like that. That's where f of xy equals 1. And then the next one would be at, what did I do, 3? Yep, so 3. And then the next one would be at, at 5, because they get smaller and smaller as you go up. So now we're looking down the z-axis on top of these level curves. And this is how you make a topo map. To take a 3D symbol and smash it down into a 2D. Okay. All right. Here's another theorem, a favorite of mine. If f is differentiable at some point x naught, y naught, and the gradient at that point is non-zero, then the gradient, not p, the gradient of f is perpendicular to the level curve of f through x naught, y naught. Okay, so check this out here. I'm going to keep this picture up there because it'll be fine. All right. I'm going to put come back. All right, on this level curve here, I'm going to put this point here. And that's where P naught is, x naught, y naught, okay? So right there, perpendicular to it, is the vector del f evaluated at P naught. Now perpendicular is, it changes, right? So what we're saying is if you took a little tangent here, like a t, it would be perpendicular right at that point. If I had a different p naught over here, then I would have this for my del f. So we'll call this p1. This would be del f of p1, but it would also be perpendicular to the curve. Okay, and similarly, minus del f, so it would go this way. So minus del f, p naught would go that way. Okay. All right, I have so much more to get through. I'm going to stop here. Now that we've defined level curves and this idea of perpendicularness, and make another video to sort of hammer this home and get some more pictures in there to talk about. I also need to do a proof of this theorem, which I don't do a lot of proving in this course, but this proof is actually what you call constructive, and it teaches you via the proof how to solve problems, and that's really what we're concerned with. So I'll start the next video with the proof of this theorem, and then we'll just go from there. Oh, let me assign homework. I can't believe we're on homework 6. I already assigned the first part, so here's the rest of it. 4.5, 2, 7, 12, 15, 27, and 39. The first part was 4, 12, 26, and 42. I don't think there'll be more for Monday, but there might be. And if there is more, it's going to be because I want to work in 14.5 a lot. So we'll see where we get with the next video and then go from there. All right, see you in a bit.